Hello guys and girls and welcome back. Well, today we're going to be doing a simple homework called Maze 1, one of Dr. Schwarter's favorite homeworks. So before we get started into this, let's see what the instructions state. So currently we are given a header file for solve, vertex header file. Keyword here, this vertex file, you don't need to implement it. You can modify it, but if you modify it, just get rid of it and put it inside your solved header file. We have our test case and mostly just that. So we're given a string, which is this, and we have walls with open spaces. So our walls are going to be our hashtags, and our vertex are going to be the open spaces. So we're going to try connecting them to find our shortest path. So very simple solution here. So for example, right here, we need to find the shortest path. We're given this, we solve it, but if it chooses the longest path, that's incorrect. So let me see if I can try to explain this homework to you guys. So let's get started to it. Alright, my tablet just told me I have no battery. So let's get started into this. So first things first is creating the vertices. So let me give you guys an illustration on what these are. So we have these walls. And we're gonna these are your hashtags. Are we gonna make these into vertex? Well, no, because there's no point in having them in our solution. If they're not vertices, we just ignore them until there's an open space. So for example, right here, these are gonna be my vertex. I'm gonna add it into my unordered map. So first things first is, what am I gonna do? All right. The first thing I'm gonna do is I'm gonna create an unordered map with my key having anything that's related to the location of your map. So for example, I have it. You can put it as a string or you can put it as an integer. So how would I say this? Each location here has an ID, so you can find it. So for example, this is row 1, 2, 3, or if you want to do it in an array way, 0, 1, 2. And we have over here is 0, 1, 2, 3, 3, 4. So let's say I have this vertex at location 1, 1, 1. Let's use arrays here. 1, 1. So what you can do is either make it a string where it says 1, 1 location. That's going to be your key. You can also do some sort of math. A common thing I do is I multiply my row by 100, so row times 100 plus my column. So it's going to look something to this. This 101 would be 101. Alright, so that's going to be my key. For value, it's going to be my vertex. So anything, for example, this is going to be my vertex in my unordered map. So you can do something like unordered map, integer vertex, and then call whatever vertex set that you're working with. Alright, so you guys get the gist of how I'm getting these vertex into my unordered list. Alright. Now, once you have this unordered list set up, declared, you would first iterate through the whole maze. So what we're trying to create here is all of these locations. So let's do this. Hashtag, 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 and hashtag, hashtag, hashtag. So I'm gonna do this for right now. And this is my exit point. This is my starting point. So, this is a string, so do whatever you guys do with strings. What's the size of the string? And iterate through it via x. Every single time you find an empty space, which is just a character of nothing, you would create the vertex at that location with its corresponding key. As I mentioned, like it can be a string, it can be a number, anything at all. So just create it. If not, if it's nothing. Oh, also I forgot to mention there's always new lines here. So let's do this too. Okay. So let's say you do find an empty space. You create a vertex using the vertex, and then you use the constructor that it contains with a row, column, and then I believe it's just with the index of it. I believe I add index. Yes, I add an index to my vertex. So it keeps track what's the current index of this location. Then I will use my unordered map at the current location of row and columns, and I set it equal to my new location, my new vertex that I found. Now there's another condition that an else if I hit this. So let's say I iterate through this whole list, and I found here. This means that I'm updating my rows. So let's say I'm in row 0, I hit this location, now I'm in row 1. From row 1, I clear out my column. So I make my columns 0 because I'm refreshing where I'm starting at. And then I also keep track of what's my maximum column, which is here. So keep track of where your maximum column is at. You can do like whenever you're resetting, you can just do column -1 to get this location. So only you want the max. And then once you're done with these two conditions, you do a column ++. So for example, right here, this is like pseudocode. Your if this is if empty space, else it's a new line, and then outside of everything, just do increase column because you're still moving across. You're still moving. Does that kind of like sort of make sense of what you guys are doing with these? You're basically just creating the vertex. Once you're done with everything, I want you guys to keep track of the max rows. The max rows this thing contains. So for example, this one has 0, 1, 2, 3 max rows. And mostly just it. Max rows would be -1, I believe. Not very sure, but you guys can mess around with the code. So this is just for setting up the overall vertex of every empty space, because I believe Dr. Schwaller does a different method where he uses characters, and you can't keep track of characters. But in this case, it'll work. Does that make sense, Carlos? By the way.
Yes.
Yeah, because you told me about like these sort of characters that you need to keep track of where they're located, and in this case, you can keep track of the vertex by using an unordered map with just simple math of row times 100 or something plus columns. That is one of the things I use. I've seen other students use strings and other methods. Alright, that makes sense. If you still have any troubles, you can message me. Now, assigning neighbors. So, I'm gonna reiterate drew my list. I drew my mace, I mean. Because, I don't believe in the first one I created it. Well, probably I did. So, first things first, we have to check where we're starting and ending. So, for example, right here, let's say I make this tree, and these walls. Where would my start be? Well, my start would be in this location, and my endpoint would be in this location. I need to keep track of where I'm starting and ending. So you can save this as a variable. So you can, I don't know, call it vertex start equals new vertex at 0, 0, 0, and then once you find it, you can reassign it a new vertex at column 1, 0, 1 with the current index of 0, 1, 1. So there's index 1. And then you would assign it... No, you wouldn't assign it. Else, if you find another point, an entry point, just make it your last. Now, when it comes to assigning the neighbors, that's a little different story. So, when assigning the neighbors, you have to keep track of two things. So this is your vertex, let's say. Empty space, all of that. I would need to look up and left. Now, there are some conditions that you need for it to work. I believe it's is up, right? So the condition is you don't want row to check what's up above it. So for example, I'm in this index, and let's say this index is my entry point or something right here. Then I won't be able to assign it anything above it. Similar thing with here. There's nothing above it, so I can't really assign it. So make sure that your row isn't the first one. For the column, it's a different story because you don't want to go to... You don't want to go past NN, because that's going to give you some out of bounds syntax error, which is what we don't want. So those are some two cases when checking the neighbors. Now, let's say we do pass these cases. Let's say we know we're like in the middle of the maze, so right here, and we do have a left neighbor and up neighbor. What I would do here is first, let me see here, because I use current index. So I use my maze to check if the upper, if my upper is, let's see. All right. Okay, I get it. So I need to check my upper right, my row above me. So the strategy I use is just get the current location of your index and then subtract it by the maximum columns. Just that. So you can get this guy above here. You can do other things, such as, well, can you, yeah. So this one just basically you're looking above the maze during the index, because I believe if you use the unordered set, it might give you a null pointer which you can't really use, I believe. So I just look above the index, which is this location, and I check, hey, is this an empty space? If it is, then I set the neighbors together using, I believe it's because I connect them both. Yeah. I believe it's a two-way diagonal. You just connect them both. So the vertex has this vector called neighbors, which you just push this neighbor inside your vertex, and then you would do the same thing to the one you're working with. So you're connecting them both. So basically, it looks something like this. And then this is a little bit of an illustration, but it's just should be like this because they can both go both ways. Similar process to the left. Similar process to the left. So let me just start writing here. Oh. Similar process to the checking the left neighbor is I'm just looking at my current index minus 1 because that is what I'm looking at. Yeah. That's I'm looking at this neighbor, so I check, hey, I call my vertex max. Hey, at this index that I'm currently at, what's in my left? Is there something there? And if there is like a hashtag, don't do anything. If there's a like empty space, hey, I want to connect these two neighbors together. So I'm gonna push this neighbor into this one and push this neighbor into this one. And how you're gonna push them is you have this vertex set that you can use. And right here you can do vertex dot at row. Well, you just get this guy's row and column. It depends on how you're setting up your key in your vertex. So what I can tell right here, this is my current row and my current column. This one's my current row with my column minus 1. And similar thing with above, it's my current row, my current column, but the neighbor above it, it's going to be my row minus 1 with my current column. Yeah. And then you just connect them. Alright, so any questions on this one? Like, this is just to connect the neighbors. And then once you're done, you would do the same thing you did in with your new lines. So basically, your new lines, just reset everything, increase row, reset a column, and column plus plus as you're iterating through it. Any questions on that?
No.
Alright. Now, there's an optional thing. Depending on how you set up your neighbors, you might not need to do this. But what you have to do is you have to attach start and last. But there's an optional thing. You guys don't need to do it. You could just keep track of where your start is. All right. So I believe what I do here is just assign. All right. So if you don't have your start and last attached inside your vertex set, then this is just an optional thing. If you're able to do it, you can. So what I do is just check where does my start begin? Well, my start is in row 1, or is it in the maximum row? Because if it starts at row 1, then it means it has a neighbor underneath it. If it starts in my maximum row, and then it has a neighbor, I believe, above it. Right. Yeah, it has a neighbor. If it starts at my column, which is 1, then it has a neighbor on the right. So what I'm doing here is checking where I'm entering and exiting. So let's say right here. Well, I enter in this location, and there's a bunch of walls here. So hashtags, 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 hashtags. So I know I have a neighbor up here and a neighbor down here. That's mostly what I do. Just check where you're going. If I start here, hashtag, hashtag, then I have a neighbor on my right side. If I start here, then I have my neighbor on the left side. So just what you're doing here is just you're connecting the neighbors that you didn't connect previously. Alright, that's mostly just it for that one. That's not much. So let's see what this one is. Okay. And then you just do a vertex. If you don't have them inside your vertex set, just add them by doing the key that you've been doing and equals star, which is your vertex. I didn't do it in my solution because I wasn't thinking correctly. Now let's go into breadth first search. You guys learned this in class. First things first, you make an unordered set called marked. So this is gonna be per pseudocode because it's not really an answer to you guys. You guys learned this in class. You're gonna make a queue system, you guys with a vertex type, with a vertex class inside it, and you guys can call it on a queue. You get your first. Let me see if I can illustrate this. I guess. Let's say I connect these two. I guess. And then this is my endpoint. And this is my starting point because this is kind of, yeah, I'll do this. So we have this queue. The first thing we do is we insert our source, which is S. This is our S. Okay, let me add a. I don't know what should do here to make it longer, but I'm just gonna do this for examples. We do a while loop that checks like, hey, is this queue empty? Just check for queue empty. Then we make a new vertex and we set it to queue.front. Queue.front, and then we pop it from the queue. So we pop this from the queue. That's our source. It's marked. And then we would iterate the neighbors from this source. For right now, it's just a source. So let's say I go to this neighbor. I check how many neighbors this one has. Well, I checked how many neighbors my source has, which is just 1. So I just go to this 1. And I make a new vertex for this neighbor. I mark this neighbor, and then I push it into my my queues. Then I use my breadcrumbs, and my breadcrumbs is a vertex, and my breadcrumbs is an unordered map with your key being a vertex and your value being a vertex. So let's say breadcrumb y vertex is equal to my source. So let's call it source S. And then I'll iterate through. This is gonna be okay. So I added this into our queue. Now this is the front. I check the neighbors, and then so right here I would do. I believe I'll call this 0. Let's call this 0. From here, 0. And then over here, let's say my first neighbor would be this one, for example. I add it to the queue, and then this is 1. This is an example of how to do it. Get rid of it from the queue, look for its neighbors. Well, I have a neighbor right here, and then I do here. Let's call this 2. Kill this one, pop it out. of your queue, and then right here 3, 3, 4, and then once you're done with this one, you go. Wait, I believe it's. Wait. Yeah. Once you're done with this one, you go to this one, which would be 3, and then you compare like which one's faster or something like that, and then you close it. You kind of get the gist of it. It's what you learn in class mostly. Now, what we're gonna do is you guys learned this in class. You guys have the algorithm too. So, breadth first search is this. I believe you guys have a demo here that you guys use breadth first search. Correct? Don't know. Believe it's this one. Yeah. Basically, what I'm trying to explain here is that you have source, which is A. We add it into our queue, and then we look for the neighbors. So our current X is A. We look for our neighbors, which is B and D and C. So these are all gonna have breadcrumbs of A. From here, we look at our first neighbor, which is B. And from B, we're gonna check its neighbors. So it's C. We leave a breadcrumb on E. And then we look at neighbors C and D. C and D C doesn't have any neighbors, so we leave it alone. D has F as a neighbor, so we just go with it. So right here, the C, no neighbors. And then we already know it already has a breadcrumb of A. Now D has a neighbor, which is F. We assign it to D. And then we have E, because it's in the queue. It was in the queue first, so we're assigning G to E with the breadcrumbs. And that would end our whole marked. That's why we marked them, so we don't reiterate through them again. And then you're done. So this is the algorithm you're going to be implementing on your breadth first search. Now the shortest path function, it's just very simple. I don't know if he has it here too. Yeah, kind of like the shortest path. Don't know where this is at though.
It's the directed graph B. It has like the whole code.
Yeah. We have basic edges. You know, when I was explaining to you guys the neighbors, you had basic edges. Where is it? Here. I believe shortest path. This is what you're gonna be doing. He gave you guys the code. The only difference is that you're working with the maze. So, first things first, get your vertex start, vertex last, generate your breadcrumb, and then call in breadth first search on the start with your vertex unordered map of breadcrumbs, because you're going to be using this in your shortest path. From that point, you're going to be creating your current vertex that you're going to be iterating through, and which is your last. So basically, you use start to do the breadcrumbs, and then last to trace back. Like, oh, let me find my path again. I'm right here. Now, what we don't want in your what we want in the while loop is current is not equal to start. So that's going to be the condition. And what I really like about my vertex, about having the current index, is having to do maze at the current index. And then we assign it to an O, I mean. And then we use our breadcrumbs, current. So similar to what he has in his code, where he's just redeclares breadcrumbs. Breadcrumbs, so is equal beak C, and then I'm just gonna do current. So this is kind of the algorithm, how it works. I really like this one where I'm keeping track of my current. You can do it a different way with the index and so this is my solution on how to do it, and then I just return the maze. So any questions on the whole huge algorithm, like any steps that you guys have? Alright, if
Not
there's no
really,
more
yeah.
questions, you guys can message me. And hope you guys enjoy. Just please subscribe and hit that like button. Goodbye.